About the compounds of sulfur, and in previous class we have discussed the most important compound of sulfur, that is sulfuric acid, that is H2SO4. And we have also discussed about that hydrogen sulfide, how its preparation is by the Gibbs separators, and how we can prepare that by other methods. So now we can discuss that is another compound of sulfur, that is an important compound of sulfur. Generally it is used for the estimation of that is iodine. So we'll write that it is sodium thiosulfate. The sodium thiosulfate is also called as the hypo solution. Commercially it is known as hypo solution. So we are going to discuss another that is compound of sulfur, that is called sodium thiosulfate. So it is Na2SO2O5. So we are going to discuss that another compound of sulfur. I'm going to write that as sodium thiosulfate is, that is sodium thiosulfate. We are going to write that, and that sodium thiosulfate is, the formula for that is Na2S2O3.5H2O. It is like that. That is the sodium thiosulfate is. It is also called as the hypo solution. So we used to say that it is also called as hypo solution. As we used to write that it is a hypo solution. So we write that is the sodium thiosulfate is also called as hypo solution. So that is like this. So this is about that sodium thiosulfate. We used to say that is a crystalline salt that is having a water of crystallization .5H2O. It is. Now let us check that how the preparation of sodium thiosulfate will take place. How we can prepare the hypo solution is. So if we check that the hypo solution, the preparation of hypo solution, we can write like this. The methods of preparation, we can say that is for the hypo solution, we used to write that the preparation methods for hypo solution, we used to write that it is when we write that the sodium sulfite, we used to say that. The first method we can say that when sodium sulfite is treated with sulfur, when it is heated with sulfur, we used to say that we used to get that, but it should be, and we'll say that it should be boiled in absence of air. So it should be boiled in absence of air, because otherwise if there is a air, then in that case the sulfur will get oxidized. So in absence of air, so you say that absence of air or oxygen, we'll say that we get that it is sodium thiosulfate is formed. So that is how we can prepare the sodium thiosulfate. One of the methods for the preparation of sodium thiosulfate is. We can also prepare the sodium thiosulfate by treating that NaOH with SO2, so that we will get that Na2SO3. Then we can write that with sulfur. So like that we can also write the another method for the preparation of that is. So we can write that another method for the preparation is if we treat sulfur with NaOH. So if we react sulfur with NaOH, then let us check what will happen. We used to say that when we react sulfur with NaOH, we used to get that Na2S2O3 plus sodium sulfite. Sodium sulfite plus H2O is formed in the reaction. So let us check that how we are going to get that sulfur and the sodium sulfite. We can write that it is, we say that it is like this. So we used to get that twice of this, so that we will get 6, that is like this, and we get that it is thrice of H2O is formed in the reaction. It is balanced reaction. So that is how also we can prepare the sodium thiosulfate. So these are the method for the preparation of sodium thiosulfate is. So this is sodium thiosulfate, the method for the preparation. We can write the properties is, if we write the properties of sodium thiosulfate, we used to say that it is a crystalline substance. It is a colorless crystalline substance that is soluble in water. So we write that the properties are like this. We can say that it is a colorless crystalline substance. Colorless crystalline substance that is soluble in water. Soluble in water, we can say that colorless crystalline substance that is soluble in water, because it is sodium, that is thiosulfate. So it will be soluble in water. It is used as anti-chlor. So it is used as, or you can write that as anti-chlor, we can say that. So as anti-chlor is the removal of chlorine. It is the method in which the chlorine is removed in the bleaching process when it is present on the fabrics. So we'll say that the anti-chlor means it adsorbs chlorine from the, right? That is bleached substance from the fabrics, we will say that. So anti-chlor, we used to say that to remove chlorine from the surface of the fabrics when it is dyeing. So to remove that, chlorine from the surface of that is fabrics, surface of fabrics while that is dyeing. So surface of fabrics while dyeing, we will say that. So while we used to say that dyeing, we used to write this. When we dye this that fabrics, then in that case the chlorine is present on their surface. So when it is present on the surface, that chlorine is removed by thiosulfate. So we used to write that it is used for removing the chlorine. So it is removed like this. We can say that Na2S2O3 when treated with chlorine, obviously there will be water. Then in that case, we are going to write that if there is a sodium and chlorine, obviously we know that we know that what we are going to get that is NaHSO4 plus we just write that HCl, that is liberated. So that is the product in the reaction is what we get. Now we can balance that reaction as, we'll say that the fluorine 5 times of this, then we'll write that twice of this, and we can write that it is twice. So we can write that 8 chlorine is there. So that is how we are able to remove that chlorine from the fabrics, the surface of fabrics by reacting with thiosulfate and water is. So that is how we can write that as anti-chlor is. Another property we can write is that is when Na2S2O3, that is sodium thiosulfate, when this is treated with HCl, if it reacts with HCl directly, it will get converted into, that is sulfur SO2, NaCl and H2O, that is formed in the reaction. So we used to write that when it is treated with HCl, then in that case it will get converted into, that is I am going to write that, it will get converted into, that is SO2, H2O and its NaCl. So that is how we are able to get that the reaction with HCl is, and this reaction you can see that here it is plus 2 oxidation state and this is plus 4, whereas this is 0 oxidation state. So you can say that it is a disproportionation reactions. So disproportionation reaction it is. So this is a disproportionation reaction, we can say that. Next we can write is, we can write another properties like that, this is the test. So this is what the test, we can say that here the importance of this. Note that this is the test which is given by, the test given by, that is S2O3 2 negative, but not by SO3 2 negative. So it is used to differentiate between the thiosulfate and the sulfite. So used to distinguish between the S2O3 2 negative and that is the sulfite, we used to say that, and sulfite. So that is used to distinguish between the thiosulfate and the sulfite is. So this is the test given by that. So we can write that now. We can say that if you are having the thiosulfate, that is the hypo solution, Na2S2O3.5H2O when it is heated. So when we heat this at 250, that is 215 degrees centigrade, it gets converted into Na2S2O3. Then it loses the water of crystallization from that on heating. So it will form like this. Then this one further heating at 220 degrees centigrade, you can say that. So at higher temperature than 215, around 220 degrees centigrade, it will get converted into sodium sulfate plus we'll get that Na2S5, that is sodium polysulfide is formed. So that is how we are able to form that polysulfide. The sodium sulfate and the polysulfide will be formed. That is how we can balance that reaction is. So the sodium sulfate and the thiosulfide are formed in the reactions. So we'll get that it is like this. So that is how we are able to balance the reaction. This will be, that is 4. We can write that, and that is how we will get the reaction like this. Now we can say that the other reactions like this is, other reactions we can say that when we treat this with, we'll say that when PbCl2 is treated with Na2S2O3, then in that case, I'll get the white PPD of S2O3, that is the white PPD. So I'll get the white PPD of this. The other reactions I'm writing that. Then if I react this with, suppose I write that BaCl2 is treated with, that is Na2S2O3, then in that case also we'll get the white PPD of Ba2, the BaS2O3, that is the white PPD of barium thiosulfate. It forms a white precipitate with barium chloride, it forms a white precipitate with lead chloride, it forms a white PPD with, right, other sulfates also, but we can write that if it is only, that is, we'll say that if it is lead thiosulfate that is treated with water. When this is treated with water, we used to get that. When this is treated with water, then in that case, I got that PbS plus H2SO4 is formed. Then in that case, this is a black PPD. So this is a black PPD which is formed in the reactions. So that is how we can write the reaction with this. Then formation of complex. We read that formation of complex, then we can say that of complex. Then silver solutions. We say that complex, that is, we can write that the silver salts like, we can say that AgNO3. Then it is, we'll write that AgCl, AgBr, AgI, all these silver salts, when they react with reacts with sodium thiosulfate, Na2S2O3, to give, that is, we can say that, to give, that is white PPD of Ag2S2O3, that is a white PPD. Then we get that white PPD is formed in this case. So we can write like that. It is, that is the reaction. Then I can write that even with, if we are having that, that is FeCl3 reacts with, FeCl3 when reacts with Na2S2O3, I can get a complex like this, that is FeS2O3 whole twice negative. That is the complex form. And even I can write that, that is with cuprous chloride. So I'm going to write that CuCl2 when reacts with, that is, we can write that, third one, we can write the third reaction. When CuCl2 reacts with Na2S2O3, then in that case it forms a complex, that is a white, it forms a complex that is like Na4CO6 S2O3 whole 5. This is that complex form. So with CuCl2 we get the complex like this, that is formed in the reaction. So it forms a complex with many salts like these. Then we can write that the uses of sodium thiosulfate. So we can write that what are the uses of sodium thiosulfate is. We know that one of the use is like an anti-chlor. It acts as an anti-chlor, the removal of chlorine from the surface of fabrics while dyeing. So we can use like that. Uses as anti-chlor, we can write that. So uses, we used to write that as anti-chlor. That is used as anti-chlor. We can write that another use as, we'll say that in photography as a fixer. In photography as a fixer, we used to say that. That is when AgBr reacts with sodium thiosulfate, Na2S2O3, then in that case we used to get that Na2, that is Ag, that is S2O3. We used to write that. So we'll get that twice, plus we get that it is plus NaBr. We used to get that. So that is how we are able to write that. This is a fixer. The negative is converted into the positive. That is a fixer, what you used to say that. So it is used in photography. Then we can write that it is used as iodometric and adimetric titration. It is used in iodometric and adimetric titration. Iodometric and iodimetric titrations, we say that. So it is used in the titrations. That is how we can write that. It is used in the titrations reactions. So these are the uses, we can say that, of sodium thiosulfate is. So these are the uses of sodium thiosulfate, we can say is. So that is about the sodium thiosulfate we required in this part. That is how we can discuss about the sodium thiosulfate. So the maximum part we've discussed about the sodium thiosulfate in this is that. So that is about that. We can write that sodium thiosulfate is. Now we can write that what is the, and if we write the structure of sodium thiosulfate, we can write like this. The structure of Na2H2O3. We can write that structure is like this. Na2H2O3. So I'm going to write it as like this. Sulfur, double bond sulfur. It will be O. Negative charge on this. That is ONA. I can write that. Again I can write that ONA, and we are going to write like this. So this is how the structure is. So that is the structure of sodium thiosulfate is. This is the structure what we can say is for the sodium thiosulfate is. So this is the structure of sodium thiosulfate is. That is how we can write the structure of sodium thiosulfate. So that is about the thiosulfate what we required is. So that's all about the thiosulfate what we required is. Now we can discuss the oxy acids of sulfur. What are the oxy acids of sulfur? Let us check that. First we'll write that what are the acids of sulfur is. So I'm going to write that oxo acids of sulfur. So first we'll write that the oxo acids of sulfur. So we can write that the oxo acids of sulfur. Sulfur. So if I write that oxo acids of sulfur, we know that we'll write that one is H2SO4. This is orthosulfuric acid. We know that the normal acid is called the ortho acid, orthosulfuric acid. Then I can write that if I remove one oxygen from this, I'll get that H2SO3. That is called sulfurous acid. So sulfurous acid, you can write that sulfurous acid. So you can write it as a sulfurous acid, or you can write it as a orthosulfurous acid. It is one and the same thing. So if you remove one more oxygen from that, then I'm going to write that it is H2S2SO2. Then it is called as hyposulfurous acid. Hyposulfurous acid. Sulfurous acid, we can write like this. Now if in a sulfuric acid we add one oxygen, then let us check what will happen. So I'll write that the other is, that is H2SO5. Then we'll write per sulfuric acid. So per sulfuric acid, when we add one oxygen in sulfuric acid, it will become the per acid. So if I write that HNO3 is a nitric acid, then you add one oxygen in that, HNO4 is a per nitric acid. That is how we can write that. So per sulfuric acid. Sulfuric acid, we can write that. Now I can write that another is, we'll say that H2SO4 twice, then it will remove water molecule from this, you'll get that H2S2O7. Then it is called disulfuric acid or pyrosulfuric acid, we will say that. So I'm going to write it as a pyrosulfuric acid. So this is pyrosulfuric acid. Pyrosulfuric acid. This pyrosulfuric acid is called oleum. So called oleum, we used to say that. It is called oleum, the pyrosulfuric acid is. Then we can write that per disulfuric acid, we can write that if we add one oxygen in pyrosulfuric acid, then it will be called as per disulfuric acid. So I'm going to write that it is like this. That is, so if I write that, that is H2S2O8, then it is called per disulfuric acid. So per disulfuric acid, we can write that sulfuric acid. It is also called Marshall acids. It is called Marshall acid, as we know that if we write that that is per sulfuric acid, it is called Carrow's acid. So it is called as Carrow's acid. So the Marshall acid, the Carrow's acid, like that we are able to write that the Carrow's acid is. Then we can write that the other acids, what we can write is the sulfuric acid is, we can say that is H2SO3, we have written that, H2SO2, we have written that, like that. Now H2SO3, you write that the H2S2O3, and we'll write that it will not exist as like salt. Na2S2O3, H2S4O6. So exist as, because it does not exist as an acid, they exist as salt. Then they can be converted into the acid when it is required. So I'm going to write that it is H2S4O6. Like that we are able to write, because these are those acids which does not exist in free state. They are going to be exist like that. Then we can write that it is obviously we'll say that H2S2O5 also. So I can write that it will exist as we'll say that it is H2S2O, that is 5. Then we can write that H2, we can write that SXO5 exists as we can say that is here it is Na2. So Na2, right? Na2, because they are existing as a salt. So I write that Na2S2, that is NaX and O. You can write that it is 5. So you can write that X and then we can make it at that is 6. So they will exist like this, that is they will exist like this, where X is 2 to 6. So I'll write that where X is, we can write that in that case the value of X will be from 2 to, already we can write that like this, but it should be less than oxygen. So where X is equal to, that is 2 to 5, because number for that X should be less than the number for the oxygen atoms which is present in that. Should be less than that of, you can make of this also, but then X will be from 2 to 4. You can make for this, then X will be only 2 because it cannot be greater than the number of oxygen atom. So we can write that that is, these are those acids which exist in form of salts, but they can be converted into the acids when they are treated with HCl or some other acids which can convert this into this. So that is how the acids are. So these are oxy acids. Some are unstable and cannot be isolated. They are known only in aqueous solutions. So these are some of them are unstable and do not exist in free state. Do not exist in free state, but they exist in solution state. But exist in aqueous solution state. Solution state. So aqueous solution state means I am talking about these acids state. So these are those acids which exist in solution state 7, 8, 9, 10. These are those acids which exist in solution states in the form or in the form of their salt. Solution state in the form of their salts or in the form of their salts, we'll write that. So that is how they exist. Now we can write the structure of all these acids. So let us check the structure of all these acids. I'm going to remove this part. So already we can write that how the structure is. Let us write that the structure of these acids is oxy acids. So I'm going to write the structure as like this. H2SO4 is known to us how the structure is. So H2SO4, it is sulfur, double bond O, you get 2 OH group like this. So that is H2SO4 and with sp3 hybridization. So next is H2SO3. H2SO3 is sulfur double bond. We can write that OH and OH. We can write like this and one lone pair will be there. Then H2S2O, that is H2SO2, we can write that. So if we write that H2S2O2, we can write that it is hyposulfurous acid. So hyposulfurous acid is H2S2O. So we can write like this, that is sulfur with OH and OH will have 2 lone pairs in this. We can write like this. So we can write that it is like this. We can say that. So in that case, that is not existing like that. It will not exist in free state. It will also exist in solution state. There should be a negative charge on this which should be resonance stabilized. So we can write like this, that is sulfur H2SO2. This is unstable, we used to say that. The H2SO2. Hypo is unstable, we used to say that. Then we can write that disulfuric acid H2SO5. So H2SO5, it will be like this then. That can exist very easily. This is OH, and here it is the peroxide bond which is present in that. So this is that peroxide bond which is present in that. Then we can write that oleum. So we'll write that H2 is 2O. We'll write that it is 7. Then I'm going to write that it is like this. That is, you can say that. In this case, it is like this. We can say that is double bond OH, and I got that it is OH, double bond O and double bond O. So that is sulfuric acid. Oleum is. Now, if we write that H2 is 2O8, then we'll write that there will be a peroxide bond between those sulfur atoms. So I've got the structure like this. This is the structure of this. That is the structure of this is. So this is how we get the structure of Marshall acid is. So this is how we can write the structure of these acids. Now if I write for this, we know that how the structure is. So I'll write that in case of H2 is 2O3. So I'll write this as S double bond S, that is O negative, and it will be double bond O. So that is like that structure is, as I've written for the sodium thiosulfate. So this is the structure of this. Now if I have H2 is 4O6, then in that case I'll write that it is sulfur-sulfur bond. I'll get like this, and OH, and I'll get like this. So this is the structure of this. Then I'll write that H2 is 2O5. So I'm going to write that the sulfur, that is H2 is 2O5 is S2O5. So I'm going to write that it is like this. So in that case, I'm going to write that sulfur-sulfur bond is there. Double bond O, double bond O, double bond O, double bond O. One of them is OH and other is that is OH, and we'll write that H2 is 2O5. 1, 2, 3, 4. We get that it is double bond O, and H will be formed like this. So we can write that it is H2 is 2O5. That is, we can write that the sulfur-sulfur bond is. So we'll get that it's a sulfur-sulfur bond, and we get that it is like this. So we can write like this. Then it is H2 is 2O6. So H2 is 2O6. We are able to write that it is HO, that is sulfur-sulfur bond is there, no doubt. Then OH, and we'll write that O6 will be like this. So that is the structure of H2 is 2O6. So these are unstable form. These are all, we know that they are in the stable in solution state. So we can write that that is like this. So I'll write that it is, in this case, it will be like this. I have to write this as like this. OH 1, 2, 3, 4, 5. It is 5. So I'm going to write like this. It is like this. So this is the structure of this. Because what I'm writing is, there should be two negative charge. In this case, this case, this case. Because all are in form of sodium salt. So there should be two negative charges on that. That's why I've written that OH, OH for the two negative charge. So that is how we can write that the structures of these compound, these acid is. So there is the structure of these acids, the oxy acid is, and that is what we can say about that the structure of these acids. Now if we write the structure of oxides, suppose we write that the structure of oxides, we know that it is like this. To write the structure of the oxides, we'll write that like this. So if we write that structure of oxides, the structure of oxides, we can say oxides means we are going to write that for SO2 it is like this. sp2 hybridization, here also you can say that this is sp3, this is sp3, this is sp3, this is sp3. So all the acids are sp3 hybridized, you can say that. In all the cases we get that sulfur has sp3 hybridization. In all above acids, the sulfur has sp3 hybridization. You can say that. Here it is sp2 hybridized. Then I can write that the oxides, no? Then I can write that SO3. Then it is like this. Double bond O. And if I write like this, suppose, then in that case, what will happen? Then we'll write that the structure or the basis of. If it is multi-central atom, then in that case, we'll write the structure on the basis of oxidation state. So here the oxidation state is +6. It means it is a normal oxidation state. If it is a normal oxidation state, there is a sulfur, there will be no sulfur-sulfur bond in that. On the basis of that only I have written here. Here the oxidation state is +4, there is a sulfur-sulfur bond. Here the oxidation state is +5, there is a sulfur-sulfur bond. Here the oxidation state is +6. So there will be no sulfur-sulfur bond, but observed is +7. If the observed oxidation state is more than, if the observed oxidation state is more than the valence electrons, then in that case we say that there will be a peroxide bond between the central atom. Here the observed is +7. Here observed is +7, whereas actual we write it is +6. Here it is +6, the observed, and that is +6. Here it is, we used to write that. Again, there is a peroxide bond, but it is not a multi-central atom. It will be +6. So in this case, it is unstable. We used to write that, and we get that the structure like this. So that is all we can write about that acids. So S3O9, as I told you that the structure should be like this. We can write that there will be an oxygen between each sulfur atom. So I can write this like this. So that is how we get the structure of this is. That is the structure what we have. And between each sulfur atom there will be one oxygen atom. So that is how we get the structure of the oxides of sulfur is. So from this you are able to write that what will be the structure of that is the oxides of sulfur is. So that is the oxides of sulfur, and the other structures are. So that is about, we can say that the structure is. So these are the structure of the other structure. We can write that, suppose I'm having Na2S4O6. If it is Na2S4O6, then in that case I'm going to write that, or you can write that S4O6 2 negative. Then I'm going to write that sulfur-sulfur bond in this. So I'll write that it is the sulfur-sulfur bond. What I got is, here also I'll get the sulfur-sulfur bond. What I got is. So that is how the structure is. You can write that the structure in which the oxidation state of this sulfur is +5. Here the oxidation state is +5. Here it is 0. These are the oxidation states. Similarly, you can write that oxidation state in this case, that is +3 in this case, and this will have +5 in this case. This is how you can write the oxidation states. Here both the sulfur will have +5 oxidation states. Like that we can write that. Here we can write that both will have +5 oxidation state for both. So H2S4O6. So that is what I have written here. So it is not H2S4. Oh, that is a S4. I have to write this. H2S2. That is S2. I'll write that. There's nothing but it is H2S2O6 that I have written. And if it is H2S4O6, we can write like this, because then it will be having a structure, a negative charge on that. So this +5 is the oxidation state of sulfur. We know that. So that is how you can write that the structure of oxy acids as well as the structure of oxides of sulfur is. So that is about the sulfur, what we required in this chapter is. So that's all about the sulfur and its compound as well as the other reactions of sulfur is. So that's all about the sulfur. Next we can we know that how to write the structures of, because we can write the structures like this. That is, if we are having the structure of that is structure of SF6. The SF6 we can write that it is like this, that is sulfur, that is having a fluorine like this, then a fluorine like this, that is octahedral structure. We can write that. So it will have a octahedral structure, that is like this, having this is octahedral structure. So in this octahedral structure, we used to say that there is 12 90-degree bond angles in this. So 12 90-degree bond angles. And the structure of SF4. Structure of SF4 is it is like this, that is, write that it is fluorine, fluorine, then I'm going to write that it is a lone pair there, and one of them will be like this and other will be like this. So in this case we used to say that the 90-degree bond angle is 0, 120 degree is 0. So it is seesaw shape. So we'll write that as no 90-degree bond angle. 90 degree or 120 degree bond angles. Because due to the presence of lone pair, we already know that there will be no exact bond angles. The bond angles changes because of the presence of lone pairs. So that is how you can write the structures of the compounds of sulfur as well as for the sulfur. You can say that. So that is all about that compounds of sulfur and about the oxygen family. So that's all in this class. The next class we'll start another chapter. So that is all in this class.